Okay. So, here's a quick introduction to Benford's law of digit bias. Just try to stay out of the range of the computer. Okay, so if you look at the Fibonacci numbers, a lot of other data sets like street addresses, what percent of ones, guess 10%, fix it to 1/9 or 11%, it's really about 30%. And so, just in the interest of time, not all data sets satisfy Benford's law. So for instance, imagine you have a long street, going houses at number 1, 2, 3, all the way up to L. Well, depending on what L is, you're going to get very different percentages. If you stop L at 200 or 199, you've just had a whole slew of houses that start with a 1. And so you're going to get about 5/9 of the houses have a first digit of 1. Conversely, if you stop at 999, you've just had a long stretch of houses that don't start with a 1. So it's going to oscillate between 1/9 and 5/9. But if you take a lot of different houses, there's a lot of different streets of different lengths, and amalgamate them, it turns out that the answer becomes very close to the 30%. So there's lots of different places it occurs. I'll post the slides online.
Is it sort of a weighting?
Yeah, so imagine you have the streets drawn from like a uniform distribution.
You're always going to start low, though. So you have a majority of streets that are going to be the ones, as opposed to streets that are not.
Right, so depending on how you look at things, you're more likely to have streets maybe that stop at 35 houses than 50 houses, I don't know.
Right.
It depends. You might cluster your, if you cluster your streets so that they all have approximately 400 houses plus or minus 20 houses, you won't see Benford's law. But if you go over many orders of magnitude, it's not so unreasonable to see something like Benford. So in the interest of time, I'm not going to talk too much about the applications. One of them is analyzing round-off errors. Another is storing numbers on computers. And I just want to quickly go over why we have these kind of biases. So imagine I want to use scientific notation. So I have my number x. I write it as some number between 1 and 10 times 10 to a power. And that power is going to be an integer. So two numbers have the same leading digits if and only if their significance are the same. Because I don't really care how many powers of 10 I pad you by. So if I want to understand the leading digits of my number, well, one thing I can do is I just want to compare the significance of two different numbers. So I want to get rid of this 10 to the k. Well, we talked about logarithms earlier today. Logs are useful. Take the log of both sides. Products love logarithms. And when you take the log of a product, it's the sum of the logs. What's the log of 10 to the k base 10? It's just k. So what I do is, this number is between 1 and 10, so its logarithm is between 0 and 1. So two numbers will have the same leading digits if their logarithms base 10 mod 1, if the fractional parts of their logarithms are the same. So the mod 1 just means throw away the integer part, just look at the fractional part, look at the decimal part of their logarithms. And so the big idea is we have a sequence of numbers, and we say it's equidistributed if it falls in an interval uniformly. So what this means is take the numbers between 0 and 1, and take a subinterval AB. Maybe AB is the interval 0 to a half. And then my sequence is equidistributed if the percent of the time it falls in here is just the length of this interval. So this has length a half, I fall in here half the time. If it has length 2/3, I fall in there 2/3 of the time. So this is what it means to be equidistributed. Some people say uniformly distributed. Some people say it falls evenly. That the chance that you're in this interval is just the length of this interval. And so since this interval lives in 0, 1, the chance is always going to be between 0 and 1. And so it turns out a big theorem is if you choose any irrational number, then if you look at the fractional parts of n beta, that's equidistributed, that's uniformly distributed, that's evenly distributed. And we talked earlier today about how continued fractions can tell you how irrational a number is. That will actually tell you how quickly this becomes evenly distributed. It will give you some idea of how long you have to wait. So if you teach statistics, you probably talk about the holy book of statistics that tells you if thy sample size is at least 30, thou shalt use the central limit theorem without worry. 30 data points is more than enough, and we can just approximate it. The amount of irrationality of beta tells you how quickly the evenness sets in. And so it turns out certain numbers, the log of the golden mean is irrational. The log of 2 is irrational. And so, I chose a number square root of pi. And I looked at, the fractional parts of n times the square root of pi. And you can see, it's not so bad in terms of how it falls. If it was perfect, if every subinterval of length 1/10 had exactly one data point, you would accuse me of stacking the deck and choosing a number deliberately. So I wanted to make sure there was at least a little error.
It's interesting that the one that's off is off by the equivalent of what's missing.
Well, it has to be because I've got 10, I only have 10 data points.
Oh, I see. Yeah.
So on the next one, when I go up to 100 data
Just one of
points,
them, yeah.
1,000 data points, and at 10,000, you need really good vision to see a little dip there, little bumps there. So for square root of pi, it sets in pretty quickly. So a data set is Benford. It has this bias to having a leading digit of 1 if its logarithms mod 1 are uniformly distributed. And so the question is, why is this true? So when I look at the fractional parts of the logarithms, the fractional parts of the logarithms live between 0 and 1. If I exponentiate 0, 10 to the 0 is 1, 10 to the 1 is 10. Here's the log of 2 base 10. This was an old program, I couldn't do the subscript, so I had to use the change of base formula. Okay, so this is the log of 2 base 10. This is about 0.3. So if my numbers fall evenly in this interval, then about 0.3 of the time, I landed to here. Well, if I exponentiate 10 to the log of 2 base 10 is 2. So what happens is, 30% of the time when I exponentiate, I have a leading digit of 1. So Benford's law of digit bias is because we're looking at numbers the wrong way. You have no chance of convincing people that whenever you see a number, you should take its logarithm and throw away its integer part. People are not going to do this for good reason. Right? If somebody asks you, how many wins did the Red Sox have last year? You're not going to view the numbers like this. But in terms of looking at distribution of properties of numbers, things are uniformly distributed. Things do fall evenly, but they don't fall evenly where you expect. They fall evenly after this logarithmic change of variables. So again, if you're ever teaching logarithms as to why we care about logarithms, it gives us the right way to look at things. So the number 2 to the n, if you look at 1, 2, 4, 8, 16, these are Benford. And so I'm not going to go through the proof, but here's the first 60 values that I was starting to write out over there. And if you notice, these numbers, their first digits don't really change that much. It takes a long time before things change. And the reason is 10 cubed is almost 1024. If 2 to the 10th was 1024, then this would be exactly 1,000, 2,000, 4,000, 8,000. And then this would be 1 million, 2 million, 4 million. But because 2 to the 10th is not quite 1,000, it slowly accumulates. Now, interestingly, what digit do you never see as the first digit through here?
What is the first digit?
7.
We never see 7. What else do we not see?
9.
We don't see 9. And so once we go up to 60, we only have 1 9, we only have 2 7s. For small data sets like this, it's actually better to clump them into maybe groups of 3. You don't want events that have probability less than 5%. That's one of the things they teach you in statistics. It's so rare that you don't have enough data points. So if you clump these together, it's actually not so bad. And so again, what's really going on here is 10 to the third is almost 1024. How many of you have seen chi-squared values? So chi-squared is measuring the goodness of fits. And so I chose 3 of my favorite irrational numbers. The Euler-Mascheroni constant gamma, e, and pi. The larger the chi-squared value, the worse the fit. And if you notice, pi has a very high value, gets a little bit lower, gets high again, gets low, gets high. Pi's all over the place. The other numbers are getting really bad. So I remember, was one of the two of you was impressing me with digits of pi? Who was it? Okay. Can you give me digits of pi squared? Pi cubed? What you really need to do is when you look at the plot of the, I'm doing a plot of the log of the chi-squared. And so the blue is e, and the red is from pi. So I'm looking at the first digit of pi to the n versus the first digit of e to the n, and seeing which one is closer to Benford. It turns out they both become Benford, but e to the n becomes Benford a lot faster than pi to the n. And the reason is, if you go far enough, pi to the 175 is approximately, there's the approximate, 1.0028 times 10 to the 87. So it means every 175 times you increase n, you almost return to where you started, padded by 87 zeros. Almost. You're off by 0.0028 ... And that small little bit will eventually accumulate, but it will take a while to accumulate. If you look at the plot of how much we're missing Benford by, approximately how big do you think each of these red cycles are? About 175. And you can really see what's going on here. So I thought I would end with some applications. This is the tax return from 1989 for somebody named William J., married to somebody whose first name begins with an H. They might have one daughter. Yes, they have one daughter. She's 12. One of my colleagues says it's amazing what the Freedom of Information Act will get you. And so you can look at some of the stuff here. So one of the big applications of Benford's law is detecting tax fraud. Individuals are safe. There's not enough data points on your tax returns, but big corporations with a lot of data, very easy to find nefarious dealings for stuff like this. And the reason is people are horrible at creating random sequences. So in a probability class, you'll often say, half the class flip a coin, half the class just make up your coin flips. And as a professor, you can tell the difference. Most people know to have about half heads, half tails. But we talked about this last time, you don't really know how many heads in a row should you have. And that's the fact that most people miss. So, an audit of a bank, and I think this is a good way to end the class, revealed a huge spike of numbers with first digit what? Got 9 choices. Nope.
7.
Nope.
2.
No.
3, 4.
4, yes, 4.
Got it.
Yes, yes. A lot of 4s. So they investigated further, and a lot of the second digits were what?
I mean, odd.
7.
A little higher.
8, 9.
Yes, 8 and 9. A lot of 48s and 49s.
Oh, trimming off from 5.
So this goes back to something we were talking about earlier. So Linda, you said you had a credit card that was being used incorrectly, and the bank eventually canceled it, and suddenly you were held liable.
No, the bank didn't notice.
Didn't notice, but normally if somebody has stolen your credit card and you report it, or the bank notices, you're not liable for the expenses. So the bank, the bank covers it. You're the bank. Somebody has run up $35 in charges. How much money are you willing to spend? How much time are you willing to spend to track down 2 teenagers who charged $35 at the 7-Eleven? 0. Somebody spent $28,000 on the credit card. How much money are you willing to spend?
A little bit.
A little bit. Somebody spent $95,000.
A little bit more.
A little bit more. And so banks have an internal threshold. Any expenses below a certain amount on a credit card that's been reported stolen, it's not worth investigating. We'll just write it off. Any expenses above a certain level, well, now we're talking real money, we'll have an internal investigator look. What do you think the bank's line was?
50.
Actually, 5,000.
Well, and also, if it is a small little thing, they'll
Right.
just be like, okay, then
Yeah.
not make you pay it. Like, if you call up,
Right.
if I have a
Yes.
card from a store and I say,
Yes.
oh, I thought I sent it in, but apparently
It's-
I have late
right.
charges,
It's-
whether online or not, they'll say, okay, we'll get rid of your late charges.
Yes, exactly.
So it's not a lot of money,
It's not worth the hassle. It's not worth the hassle for them for a small amount of money. So they traced this to one person. Most of the boost was coming from one person. What he was doing is he was having his friends sign up for credit cards and run up bills, and then the friends would call, and if they got him, they would say the card was stolen. They would say, "Oh, I'm so sorry to hear that. I'm canceling your card. Don't worry about any of the charges." And if they got somebody else, they would just say, "I'm just calling to check what's my balance." And so they would wait until their friend picked up the phone. And so they were using this, they were staying just below the trigger. The trigger was $5,000. And as long as they stayed below the $5,000, the person at the bank, at the credit card company, could just write it off without having to file any superior reports. And it was detected by using Benford's law. So this is one of my favorite examples of using elementary mathematics to great effect.
So they should have made more charges in the 1,000 range?
In the 1,000 range, absolutely. Going all the way from $10, $55. Clustering the numbers became suspicious. They should have spread it out more.
not that this one guy was getting so many calls for credit card fraud.
You know, again,
Yeah, that's-
Probably, we thought, coming out of one guy's office would have been suspicious.
Yeah, why
So,
is,
you know,
why is
I-
he canceling so many accounts and no one
Yeah.
else is?
They do the same thing for tax fraud too. My
Oh.
tax accountant was just telling